Hi everyone, thanks for being here. One thing we can all agree about is that storm water is not a friend. That's why we install storm drain inlets, so we can safely get rid of water away from our streets. There are many types of storm drain inlets, but today my talk will focus on the curb opening inlets. The design guidelines recommended by the Federal Highway Administration for the design of curb inlets are found in the Hydraulic Engineering Circular known as HEC, and the most updated version of it is HEC-22, published in 2009. But similar guidelines were found as well in HEC-12. The point of the design equations is telling you like how much flow is intercepted by a given inlet length for a given roadway geometry and gutter configuration. There are many design conditions for curb inlets. The one I want to talk about is the 100% interception. Like if we define the 100% interception as the inlet intercepts 100% of the incoming gutter flow to the inlet. To distinguish this design condition from other design conditions for inlets, we use the definition of an inlet efficiency used by HEC-22. The inlet efficiency is defined as the flow intercepted by the inlet divided by the total gutter flow. So if your inlet intercepts 50% of the incoming gutter flow, you say it's operating at 50% efficiency. If it intercepts 25%, that's 25% efficiency, and so on. So one of the motivations behind our study is that previous studies focused on studied inlets over a wide variety of efficiencies, starting from as low as 10%. Like they studied the inlets at the condition when the inlet is only taking in 10% of the entire incoming gutter flow. So they're starting from 10%, and you have until you get to the 100% interception we're talking about. As we can see here, this work was done in Colorado in 2012. You have many experimental points for this low efficiency design conditions, and as the efficiency of the inlet increases, you see high scatter in the data and fewer experiments. So we wanted to see, okay, what about the 100% interception? Because in some situations, like if you have an intersection in the street, you won't intercept all the incoming flow. So this is data from our study. On the x-axis, we have the observed intercepted flow in CFS. On the y-axis, we have the intercepted flow as computed by HEC-22. The line here is the match line. So any point beneath the match line shows that HEC-22 is underestimating the performance of the inlet. Any point above the match line shows that HEC-22 is overestimating the performance of the inlet. So if you look for a 5-foot inlet, all the points are underneath the match line, which shows that HEC-22 is underestimating the capacity of the inlet. We move to a 10-foot inlet, most of the points are above the line, some of them are below, so overall HEC-22 is overestimating. We move to the 15-foot inlet, we see significant overestimation of the inlet performance. So the interesting thing about our study that we didn't start the investigation wanting to look into HEC-22. As we will hear in the next talk, we were modeling some inlet designs for TxDOT. Then we were surprised to see these results. So we wanted to see, is this replicable in other experimental results? And if so, what are the assumptions that go into HEC-22 that leads to these discrepancies? So quickly, before we move into all that, let's talk about our model. We have at the University of Texas a full-scale modeling facility. The good thing about having a full-scale modeling facility is that we avoid potential sources of error due to scaling effects. So our roadway is 60 foot long, 11 foot wide. And something pretty cool about our model is that we can change the longitudinal slope and the cross-sectional slope to test different design conditions. So one of the two most common types of gutters, we have a uniform gutter. When you have one cross slope in your roadway, and you can have a compound gutter. When you have a steeper gutter slope near the curb, so the gutter is depressed few inches, so you can direct more flow near the curb. So consequently, For a uniform gutter, inlets installed in this configuration are called underbreast inlets, and inlets in compound gutters are called depressed inlets. They're really sad inlets. Okay, so particular type of depressed inlet that we studied here is what's called a locally depressed inlet. So your gutter starts as a uniform section having one coarse slope. Then, when you approach the inlet, your gutter transitions into a fully depressed gutter. Gradually, you start getting a fully depressed gutter. Then, after the inlet is over, you transition back into a uniform gutter. So that's a locally depressed inlet. You only have the depression near the inlet. You start uniform, go fully depressed, then you go back to uniform again. Okay? So to start, this is the equation provided by HEC-22 for the inlet performance. The equation computes LT, which is the length required to capture 100% of the incoming gutter flow. The length of the inlet that can capture all the flow coming in the gutter. We see from this equation, this LT is a function of the Q, the flow in the gutter, the longitudinal slope, the roughness of the roadway, and the coarse slope. The first challenge we had to face is where does this equation come from? It's not really clear in HEC-22 where does the equation come from. So after some detective work, we found the work of Izzard in 1950, where Izzard proposed this equation, LT as function of the flow and the normal depth. You plug in Manning's equation, then you got, voila, you get this. So what we see here is that HEC-22 just approximates the numerical coefficient of Izzard's study, slightly approximates it. Moving on, in the breast inlets, HEC-22 uses the same equation, but adds a modification, and instead of the coarse slope, HEC-22 uses an equivalent slope. To know where is this equivalent slope comes from, we have first to define the E node. E node is the ratio between the flow in the depressed section to the total gutter flow. So what HEC-22 is trying to do is to use one value for the slope, SE, to account for the effect of having two slopes, the SW and the SX. So if you have 60% of your flow in the depressed section, HEC-22 assigns 60% to this slope and 40% to the coarse slope. It's just like a linear combination of the two slopes. So we'll go into details about the assumptions that go into depressed inlets, but we performed a similar analysis for underbreast inlets, and we'll show just a brief summary of underbreast inlets at the end. So for depressed inlets, the first assumption used by HEC-22 is that there is a linearly decreasing water profile along the inlet length. So you have your water coming from this direction, meets the inlet, then it starts, the water profile starts decreasing linearly. That is the assumption. In our lab, we measured the water profile, and this is for a 15-foot inlet. As we see, there is a rapid drop in the water profile. Then you have almost for the most of the inlet length, almost no flow. Really, really shallow water sheets along the inlet length. For the 10-foot inlet, we see we are getting a bit closer to the linear, but we are still far. For a 5-foot inlet, we see we are getting closer and closer. So the assumption of a linearly decreasing water profile overestimates how much flow your inlet is taking. But if we look here, we see underestimation. So this can't be the only assumption, the only factor leading to this. There must be a conservative assumption leading to underestimation as well. That leads us to computing E node. So as we said before, E node is the ratio between the flow in the depressed section to the total gutter flow. So if you have a locally depressed inlet, the gutter near the inlet is not a clean profile like this. It changes from a uniform gutter until it becomes a compound gutter. So you don't have a clean horizontal line like this. You have a transition non-uniform flow in this area. It can be challenging to estimate how much flow is in the depressed section. So what HEC-22 decided to do, it's a really smart idea, is to say, okay, we're going to compute E node based on the uniform gutter. So we are going to compute it. What is the flow in this section? That later on will be depressed. We're going to use the uniform gutter geometry to determine E node. What this implies is that HEC-22 is assuming that the local depression will not direct flow towards the curve. that will, the flow that started in the width of the gutter will remain there, and that's the flow. Only that will go to the debris section. So we did some measurements. For the same experiment, we measured the spread of flow in the direction perpendicular to the curve at 2 locations. At the uniform gutter with the black line, and immediately at the inlet, when the transition ends, and we are at the fully depressed section. As we see here, the uniform gutter always has a higher spread compared to the gray or the spread at the inlet, which shows that the flow is being spilled towards the curve, is going towards the curve. Like E node is increasing from the initial value that you get by using this geometry. To have a, this is a measured water profile in the direction perpendicular to the curve. We see that the flow is being spilled inside the depressed section, and there is a break in the water surface along the depression. And the hydraulics can be a bit complex here, but the conclusion we're going to get from this is that the way we compute E node is being conservative. We're being conservative in the value of E node we compute. The third assumption we wanted to examine is SE, the equivalent slope. HEC-22 tries to account for the existence of 2 slopes, the cross-sectional slope, SX, and the gutter slope, SW, by 1 value. So we said, okay, let's see how does this idea fare. So we use the observed flows, we plug them into HEC-22 to get SE, the equivalent slope. And from the equivalent slope, we computed E node. Because E node has a physical meaning, so we can evaluate it. How valid is that? And we have the histogram of the values of E node here. What we see in this histogram is that E node sometimes have values of 0 or negative, or more than 1. So the flow in the debris section can be greater than the flow in the total gutter section, which is physically impossible, or the flow in the debris section can be negative or 0, which again is physically impossible. So the idea of using 1 slope to account for the effect of the 2 slopes, we might need to think about that more. All right. So now we'll talk about the potential problems that talk solutions. So collected data from 6 studies. We have 118 experiments. Here we have the observed versus the computed flow. As you can see, each color is a different study in the literature. And we have some underestimation, and we have some overestimation over here. I don't have time to get into this graph, but what it says quickly is that as the length of the inlet increases, we move from underestimation to overestimation. The gray dots, as the length increases, we get to overestimation, blue dots. For the same study, you move as the inlet increases, you change from underestimation to overestimation. So we wanted to have a new design procedure that's simple to use. So we decided, okay, you compute HEC, the flow intercepted, using HEC the same way you do it. It's an iterative procedure, we don't want to mess with that. Then after you compute it, you multiply the Q by HEC, the flow by HEC, using a correction factor. And the correction factor is a function of dimensionless parameters that you can calculate while you are computing Q HEC. Multiply the two, you get the Q expected. And the data we use to derive this correction factor comes from inlets from different sizes, from 1 foot to 30 foot length, really flat and really steep longitudinal slope, again and cross-sectional slope, again really flat and really steep, and different gutter geometry, depression and width. So that is after applying the correction factor. This is before, this is after. We notice a big decrease in the scatter. So the R square increased from 0.72 to 0.91, and the root mean square error decreased from 1.46 to 0.39. That's almost a factor of 4 in reduction of the error we see here. Right? Now to move quickly to underbreast inlets, we collected data. I like collecting data. Collected data from 5 studies. I have 117 data points. The inlet length from 1 to 35 foot. If we look at this graph, we see that HEC-22 underestimates the capacity of the inlet. And if we zoom down here, at these points, we see almost the same trend. But this is all within 25% error, which is not bad. And the underestimation is most pronounced for steep cross slopes, of 4 and 8 cross slopes. So like the summary of this is that like for underpressed inlets, HEC-22 does fair job, and underestimation is especially pronounced for steep cross slopes. And we digged into the assumptions to see where does that come from. All right, so another observation, something we came across while analyzing the data, is if you have a really steep longitudinal and a really flat cross slope, something happens here. The flow doesn't want to fall inside the inlet. The flow just like wants to keep moving forward. So for underpressed inlets, these are full-scale experiments done in Stanford University. So if you have a flat longitudinal and a flat cross slope, things work fine. You are really close to the match line. However, if you have a flat cross slope and a steep longitudinal, you have huge overestimation, and the 100% interception doesn't even occur. Like the flow just escapes the inlet, doesn't want to fall down inside the inlet. We see this again in the breast inlets, and like even after you correct it, like the correction makes things a bit better with the gray dots, but still like you see this huge overestimation. So like we still are not sure like why is this happening? Is this because the flow is really shallow when you have really steep longitudinals, that the evolution of the boundary layer is coming to an effect, or some forces like surface tension is now like important? We still need to think into that. So a good rule of thumb we came up with is that if the ratio between the longitudinal to cross-sectional slope is more than 2, then maybe use a combination inlet, or like use a grade inlet, something, a different type of inlet in these situations. Conclusions? So for locally depressed inlets, assuming the main assumption that goes here, assuming a linearly decreasing water profile really overestimates how much flow your inlet is taking. And overall, HEC-22 underestimates performance of short inlets and overestimates for long inlets. And we managed to come up with a correction factor that reduced the error by a factor of 3.75. And for underpressed inlets, HEC-22 does a good job in predicting. Finally, we recommend using a different type of inlet if you have like a steep longitudinal and a shallow or a flat cross slope. Like something special about HEC-22 equations is that really ambitious and really general. Like usually each DOT will like do experiments with a specific design of the inlet and then come up with charts for that design. HEC-22 had the ambition of making a generalizable equation. So that is something we should all get behind, and like eventually we have something like this. So with that, I would like to acknowledge my advisors from the University of Texas. Professor Ben Hodges is here with us, and Dr. Michael Barrett, and Frank Shala, my previous lab partner, for being a good friend and a really like great lab partner. And finally, TextDot for funding our research, so I will not be homeless. And with that, I will take any questions other than how and why am I inside the Curve Inlet. Thank you.
My name is Mumaindi. I'm the Director of Applied Research Innovation Branch within the CDOT. And we had an extensive research on the inlets. Prior to our research, in our design manual, the interception rate into these curved inlets were based on the wear in orifice equation. But I initiated a research project with the University of Colorado, and we have a huge area, we call them urban drainage flood control district, which is about 13 counties and city, as well as Colorado State University. We did a full study. We didn't downsize them. A full study. CSU is probably the largest, hydraulic lab in the region, and we did all the study for 13 different inlets, not only the curve opening. And the curve opening, we call them type R inlet. There was a hydraulic guy in CDOT, a rice back, and he developed the inlet, and that's what we named him, the rice back. So we did them for type R inlet, which is curve opening inlet. We did them for type C, type D, vein grade, and all combinations. And Dr. Go is from a professor at the University of Colorado. Ken McKinsey is the head of the urban drainage flood control. So we did a study. So what did you find different than what we have already found?
Okay, thanks for the question.
And how can we, update our study?
Right. Thanks for the question. And like indeed, the Colorado study was a comprehensive study for different types of inlets, particularly different designs of great inlets. We have horizontal bars in different situations. So there are two differences here. First is that we focused on the data points here. While in the Colorado study, like you covered a lot of data ranges of the efficiencies. But what we really focused on is this part, the 100% interception. Second difference is that in Colorado, when we contacted, I think we contacted group, and you studied like inlets with continuously depressed gutter. Like you don't have just a local depression, you had the gutter is depressed, then you add another depression near the inlet. So like it's slightly different configuration than the one we are dealing here with the local depression. Okay, so like these are the two differences, and for the study you try to calibrate the coefficients in HEC-22 to match the design of the inlets that you have. That's the work here. Like you have here the HEC-22 and you have a fitted equation. So it would be great to initiate a dialogue with the Colorado University and see, okay, how can we like expand the work we did here to cover like the bypass flow and the continuously depressed gutter. So like there's some overlap, but some areas that Colorado covered that we didn't cover it.
The reason we don't want to have a 100% interception rate on continuous slope, because it became very, very expensive. They are 10,000 to 25, 30,000 per unit. The only area that we recommend to have a 100% interception rate in the sag vertical curve. That's the only area in our manual that we have to intercept 100% of the, of the flow. On the longitudinal slope, in different cross slope, 100% interception is very, very expensive, and so it's not really, we don't recommend that.
Like different states can have different like storm patterns or like different needs. So like it's good to have this and also have to know what's happening in this part. Yeah.
One more question. Just a quick, I'm Cornel Kearney for Highway Research. I noticed your flume had no instrumentation carriage, and you're dealing with very shallow flows. How did you measure the flow depth?
So like we have like the photo doesn't show it, but we have like how to say it, the point gauge. We have it like we have the like it spans the point gauge, spans the length, and like yeah, we have it. We have it installed. We can like have it installed.
Okay. Thank you.
Yeah, sure.
So I understand there may be some more questions, but just to keep things moving along, and we keep going, and just hold them, and we'll wait till the end of the session, and we can entertain questions there when we have time, or you can approach the speakers afterwards. Thank you very much.
Sure.